So generally speaking, in functional programming languages like Haskell and many others, we've got a dilemma when it comes to programming of graphics libraries, animations, games engines, these sorts of things. So we can either use an existing state-of-the-art framework and use its probably object-oriented imperative API bound via foreign function interface and write something like Objective-C code, but in Haskell. Or we can use a native Haskell solution with graphics coded up from pixel by pixel, maybe have a slightly suboptimal graphical representation, but nice, pure functional code. Well, the question is, can we somehow take an existing state-of-the-art framework and wrap it in a manner that we can still have this nice algebraic, purely functional API? And that's what this talk is about. It's not that we couldn't write a library like this in Haskell from scratch, but doing this is just a huge engineering effort which people in practice are not going to go through. So what we want to do, we want a nice functional API and then a translation layer which transcribes operations on that functional API into changes in the underlying object-oriented imperative framework. So the way we are going to do this, we are going to look at what's the state of the art, how do these frameworks work these days, then what's the functional interface we would like to have, and then finally, how can we bring the two together. And to keep this talk concrete, I'll use two concrete examples, the SpriteKit library, which is Apple's framework for animations, games programming on all of Apple's devices, and a little game which may seem familiar. So let's have a look at the state of the art and this game. So you know the original version where you are a little bird and see there's some tilting, there's animation, pipes coming in, some physics, collisions, stuff like that. So we have to handle all these things. So how is such a scene represented in a framework like SpriteKit? Well, we start with the scene object, and then below that is a scene graph, composed out of a variety of different types of what are called nodes in this tree. And there are nodes which have a visual representation, such as the sprites, but there are also nodes which are just to group items, and then we can attach properties to the visual and the non-visual nodes. Those properties could be actions, animation actions, such as a movement over time, or they can also be physical properties where these nodes then participate in a physics simulation, for example, to add gravity or other forces to the scene. Now, this is really in fact a graph because there are back edges and so forth, but in the rest of the talk, I'll just treat it as a tree. And that's okay at first approximation. So what are some of the challenges that we face when we want to represent this type of structure in a purely functional language like Haskell? Well, it starts with inheritance, no surprise. So SpriteKit has a superclass called skNode, and below that some specialized types of nodes. And this superclass, it contains a variety of properties and also methods which are shared between all these different nodes, a location on the screen and so forth. And somehow we have to kind of represent this in our Haskell version. And then even worse, I think Apple has made a not so smart design decision by putting the scene, the overall root object, into this hierarchy as well for some, I guess, not so smart reasons. But as a consequence, in an Objective-C or Swift program, you actually have to subclass this SKScene object and probably add some game state. And in particular, you need to subclass it because the superclass in Cocoa and Copal Catch of skNode is a class called NSResponder, whose purpose is to give you access to input events. So if you want to get mouse clicks, keyboard inputs, touches on a touch screen, you need to be able to subclass those classes. And doing that from Haskell is not going to be any sort of fun. So we have to find a different way to do this. So that's problem number one. Problem number two, well, we have mutation. So for example, the bird, it killed depending on its vertical velocity. So how is that realized? Well, in Swift or Objective-C, we just go into the Sprite class, which is a subclass of sknode, and hence inherits this rotation property, which is highlighted here. And just by changing that, we can change the tilting of the sprite. Now, where is this change affected? Well, if we look at the overall picture, then we see that the root class, the scene class, includes a method update. And that's like the big hammer to change things. It's called once per frame. It's got in through its self-pointer. It has access to the entire tree, and it can happily mutate whatever it wants. In particular, it can change the rotation of all the different nodes. Now, this is certainly an extremely non-functional way of performing this kind of change. So we'll have to have a different story here as well. Well, but it gets worse. It's not just that visual properties or locations, positions are being changed. The entire graph changes. If we look at how these pipes come into the scene and float out of the scene again, well, that's new objects which appear on the screen. And the way this is realized is that, again, sknode contains a few methods which lets us edit the structure of the scene graph. We can add nodes, we can take nodes out, we can rearrange nodes. And again, it is from this superclass, this case, scene object update function, where we can just go into these different nodes. And then what happens in this scene we just saw, we've got one set of a pair of pipes, and then another one is added in one frame, another one is added in another frame, and then eventually one set of pipe will move out of the scene. So all these graph edits we have to represent somehow. So just to summarize so far, we have got three types of problems. Firstly, there's the subclassing. Somehow we haven't got any inheritance in Haskell, but we have to kind of deal with the shared properties and methods, and that we need access to these input events and so on. And then we have mutable properties, and even worse, mutation of the entire scene graph. And we want to represent this in a purely functional language. In fact, we don't even want to use anything like an IO monad or anything like that. Okay, that would be easy, and lead to code which is essentially like the imperative code. We don't win anything except funny syntax. All right, so let's have a look at what do we want. Well, with respect to the subclassing, if we look at this particular setup, and really we can ignore the scene class because it really shouldn't be in this hierarchy in the first place, then really what we got the base class, sknode, with all those shared properties, and then we got something like a sum, right? A node is either a label, or it's a sprite, or it's an effect node. I mean, these are all alternatives. So let's represent it as a sum type. Easy enough. We use Haskell's record syntax, and we've got one variant for each. And for those of you familiar with the Haskell record syntax, you may know that within different alternatives of one algebraic data type, of different alternatives of a sum, you can actually reuse the same label. Which means if by convention, in this case, we do this for every alternative, we get a similar effect as that of the base class in the class hierarchy. So something like name, position, and so on. These are shared fields throughout all alternatives. That's what what in Objective-C is in the SK node superclass. And then every alternative but the plain node alternative gets its own alternative specific fields, such as the label class, which has a label text which is being presented. All right, so first problem kind of solved, but we still haven't got access to the input events. Well, that's going to be solved in the next part, but we still have to take care of the scene. The scene which used to be in the hierarchy we took out, so we turn it into its own data type. And it contains a list of nodes, which are the different nodes in the scene. And as we will see later, the other variants of the node type can have children as well. So to get this tree structure. And the scene class is parameterized by two type arguments. And that's our way of representing the extension of local state, which is usually game-specific state, in a functional manner. So as you can see, this scene data is used in this field, and the children's node data type refer to the second type parameter. So we've got a way of parameterizing all the nodes and the scene with game-specific state without performing any subclassing. All right, so let's see how this works out. Well, let's go into this, and first of all, we have to define the state, which is specific to our game. So in this case, for the individual nodes, we don't need a lot of extra state, except where we spawn the pipes, because we need random numbers to have the pipes appear at different heights. So that's the list of integers up here, which is in the node state. Then on top of that, we need a state record for the entire game, and that's mostly a few different flags which represent the specific mode in which we are, whether the game is over or it's running, collision, and so on, and some information like the current score and so forth. So we add this as well. And then finally, not quite finally, we have the sprite, which is the bird, which we call lambda. And it has some visual properties. And then we've also got the overall scene, which includes, for now, the bird as its only child. And if we display this scene now, we've just got the bird flapping, hanging in midair. All right, so far so good. Well, let's take care of all this mutation. Well, now, in this algebraic data type, this is just a standard Haskell type. There's no way we can update, like overwrite, a field in the middle of a Haskell data structure. It's a purely functional language. But then the functional way of dealing with such a situation is to define a state transformer. So we change the type of the update method, which now becomes an update function. So this is part of the scene description, that this can have an update function. And what's the type of the update function? Well, it's a pure function. It takes a scene description, a record, a time interval, which is just how much time has passed since the last invocation of this function. And then it returns another scene. There's no changing of the old scene, which would be the imperative approach. Now we return a new value, which is a representation of the new state. That is exactly a state transformation function. So this is, if you like, the straightforward functional and the most elegant and simplest representation in a functional language. Okay, so what about those invariant handlers? Well, we can deal with that in exactly the same way. The scene representation, in addition to this update function, also contains optionally an event handler function. And that function, it gets an event, which is a representation of an event like normal in Cocoa. And then it just, in this case, it doesn't get the scene, it just gets the game-specific and polymorphic in this definition scene data, and it may return a changed version of that. Why maybe? Well, this has to do with the setup of event handling in Cocoa, where we can decide whether we want to handle a specific event or let it bubble up in the responder chain. So we've really turned this into a purely functional API. So let's use it in our little game. So for the moment, the bird just crashes into the ground, so we haven't got any event handling. We need an event handler, and whatever events happen, we need to kind of be able to push the bird up and tilt its position. So we're going to add some code, and the first bit of that is the event handler. The event handler gets an event. If it's a key press event, then we take the game state, and this is record update syntax in Haskell, which, given it's a purely functional language, doesn't mean overwrite the field called key pressed, but it means make a new version of this thing where that one field's value is replaced by that new value. But the old one exists as it did before. So no in-place update, but we just create a new, slightly modified version. So given that event handler, it records this key press in the game state, and then in this update function, which is the big hammer to update stuff once per frame, we can make use of the fact that a key was pressed and call a function which adds some upward velocity to the bird to pump it up. And also, if no key is pressed, then we have another function called tilt lambda. So what's that doing? Well, it has to do the adjusting the rotation of the sprite independence of the vertical velocity of the bird. And so to do that, we do some arithmetic to calculate the exact angle. And then again, we have a record update where we take the current sprite representing the bird and we alter its rotation field. And again, the same idea. This is a record update in Haskell where we take the old record value, generate a new version of that with one field modified. No overwriting of anything. Okay, and that then works quite nicely. We can suddenly kind of keep the bird up and it tilts as it's supposed to. Now, finally, how do we deal with graph edits? I guess you probably saw where I'm going. And really, I'm doing the same thing all over again, because just like the scene, all the different node alternatives have lists of children, which are just other nodes. And if I want to change that, well, I do record update, a purely functional record update. So for example, if we here we've got this situation, its game is nearly done, but there are no pipes yet. All right, so we have to be able to add new pipes to the game. We do that in 2 steps. We add an action. These are these actions which can optionally be added to nodes in order to implement animations. We add an action, a custom action, to a specific supernode for all these pipes, and that's this spawn pipe pair action. Now that's a custom function which is applied to the node from which we hang the pipe pairs off as children. So what's the code for adding another pipe pair? Well, quite simply, it takes the current node with all the pipes attached, which contains a list of children, and then this is list consing in Haskell. So we add a new element in front of that list of children, which are pairs of pipes, which is just a new pipe pair coming in from the side of the screen. So again, a record update, taking the old value, producing a new value, which is slightly modified. So at this point, you may say, depending on your exposure to functional programming, you may say, well, that's indeed how you would like a purely functional version to work. But how can this ever come together with this underlying SpriteKit implementation? Are we going to copy everything all the time, 60 times per second? Well, let's look at this object graph. So we've got this graph here, and then the update function is invoked. So the first thing we have to do, we have this Objective-C data structure. Then we convert it all over to Haskell. Now this is a small gray, again, so it's a small graph, could be much bigger. Then we run the spawn pipe pair function, which we saw on the previous slide, which takes the list and adds another list element in front. Okay, so then we have to turn all this back into an Objective-C data structure, and lo and behold, the new list element turns into a new subtree during this marshalling process, but we still got this old, like the previous pipe pair which was already on the screen. Have we just taken this representation in Objective-C, turned it into the Haskell data structure, only to recreate it in Objective-C land again? Sounds like a bad idea, doesn't it? In fact, it's a really bad idea, because not only is it slow, obviously, it actually wouldn't work. Why? Well, these types of frameworks, not only SpriteKit, but in particular SpriteKit, they typically contain quite a bit of hidden state. So for example, if you attach an action to a node, which takes a node and moves it over 1 second in a smooth animation from one place to another, then for many, 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 many frames, SpriteKit has to keep track of what, where, how far has this animation progressed, does it have to be accelerated, deaccelerated, there's a lot of information. And all that is in hidden fields which are not part of the public API. So if you take a node which has got one of those actions attached, and we just turn it into a Haskell data structure, losing all that hidden state, turn it back into an Objective-C structure, then we lose all of that hidden information, and our animations will be interrupted or reset, or like lots of weird graphical things will happen. So, and then of course it's horribly inefficient. So we have to come up with a better plan. So what's the better plan? The better plan is as follows. Let's be smart about this. So we've got our structure in Objective-C land, and we want to implement this pure Haskell function, the StateTransformer, which takes a Haskell scene description, turns it into a new value of that scene description. So we don't just marshal everything over. Remember, Haskell is a lazy language. We don't want to do work we don't need to do. So we only marshal those bits of the data structure which we actually need in Haskell. Now you may ask, how would you know? Well, you don't know a priori, but generally with lazy evaluation, you don't know a priori, so maybe we can figure that out. Then we apply the pure Haskell function, getting a new value, and then in the library layer of the binding we are just constructing, we compare the two. We check out what has actually changed, only to apply those changes in place to the underlying Objective-C data structure. Okay? So we play a game of pretend with only those bits of the graph which we need in this particular frame of the pretense. Sounds like magic. There's this big problem about magic is you always pay one way or another. So it's time to pay up. So how could we do this lazy marshalling? Well, in principle, we've got this structure. We want to marshal it over to Haskell land. So we take the topmost node, and that alone, we make a Haskell value out of it. That's a value of the scene type. So what about all the children and all the properties belonging to that node? We don't want to marshal them yet, because maybe we don't need them. So the generic solution to this problem in a lazy, non-strict programming language is create a thunk. So we create a thunk and not yet evaluated representation of what we would like to do if we are ever to require that value. So that representation of that computation will have pointers into the original Objective-C structure so that we can marshal other bits as we need. And we do so this is for the children, which is really bits of the graph which we are representing, but we do essentially the same thing for all the data values, only that we just refer to the original node. We don't marshal the name over yet. We just create a computation, a suspended computation, which could do that if we ever must. So how do we generate such a thunk? For an operation which essentially has to do FFI calls, memory allocation, stuff like that. Well, this is where the paying the price comes in. We use Unsafe Perform IO. So what is that? Well, for all the Haskellers in the room, you know what that is, and that you're not supposed to use it. For everybody else, well, it's basically saying, well, let's just forget about this pure functional stuff for the moment, do some systems programming, because we've got some inline Objective-C code in here, which we just want to package up into a representation of a suspended Haskell computation. So how inline C? Well, if you're interested in this, I had a talk 2 years ago at the Haskell Symposium explaining how to write inline Objective-C code in Haskell, and that's how this library is implemented. But it's secondary to what we are doing here. So that's the trick. All right, so that's the lazy marshalling. We create thunks, and we put them in there. If they will ever be used, the marshalling of that value will be false. So how about the diffie? So we've created this structure with lots of suspended values. Then we perform the update function, which will touch some of them. It will evaluate some of them to inspect them, and it may change some of them. So in this case, we change the name. So what we want to do, we want to somehow compare those two versions of the scene value, figure out what's different, and take all the changed values, and only those are going to be updated in the underlying Objective-C structure. So how could we possibly do that? Metric payment number 2. Even worse, really unsafe pointer equality. What does that mean? This is part of like the low-level guts of the Haskell compiler's runtime system. What it means is, well, what's the address of the original version of this thunk? What's the address of the name field in the updated data structure? Are these two addresses the same? If these two addresses are the same, that field hasn't been updated. If they are not the same, well, it may or may not have been updated. Maybe there was some garbage collection or something. Point is, only then we do update that value in the Objective-C representation. So what if that test, because it's really unsafe, came out wrong, and the pointers are not the same, but the value actually is? Well, then we do some extra work. We update a value with itself. That's semantically benign. It's just a few wasted cycles. Okay? So we are semantically on okay grounds. But this is an optimization, and sometimes it doesn't optimize. All right. So then for the last, Ryan?
Oh, if you don't mind questions.
No, I do not.
It's very similar to the virtual DOM setup, where you diff the virtual DOM with updated infrastructure. I'm curious if any of the systems with virtual DOM do this laziness trick with respect to hitting.
So your observation is, of course, 100% spot on. This is related to how React or Elm work. The difference is that both React and Elm use a view function, which is in every changed version of the view function presents a different view, and then they're clever about which parts of the view to redraw. They, as far as I know, don't do any of the lazy marshalling because the view is basically generated afresh each frame. And why is it different? Well, the difference is really, I believe, between an animation framework and a UI framework, where in an animation framework you are not in this 60 times per second animation loop. Hence also representation of these scene structures and UI structures is somewhat different with where you keep application specific state and so on. Jeremy?
Can I ask another question?
Sure.
Does it really follow that if the pointers are the same, the structures haven't changed?
Yeah.
So garbage collection won't, if you change something and then there's a garbage collection, can it not go back in the same place?
No, this can't hurt us because there are a few reasons why this is not a problem. The simplest one is we have copying garbage collector. So in the next garbage collection, no pointer will be the same because they are all in new space. Okay? Well, even theoretically, I mean, in practice, this is impossible. This is happening 60 frames per second. If you get two garbage collections, you've already lost. But even practically, it's no problem because, I mean, the new and the old objects are being copied, right? If one of them is not copied because generational collector, well, then it's a different area anyway. So you won't get false positives. Okay, so now what's the third price we have to pay? It actually looks very benign, but it's kind of the worst bit. So each of these alternatives of the scene graph description has an optional foreign pointer. So this is a reference. A foreign pointer is a pointer from Haskell land into Objective-C land. What's its meaning here? Well, whenever we take an Objective-C object, a node object, and we marshal it over to Haskell land, then we remember where it came from. That's important so that when we are deeper in the tree, we know which nodes, which Objective-C nodes to update for changes in the Haskell representation. Because in Haskell, maybe somebody just duplicated some records. I mean, there's no way to track a linearity, if you like, in Haskell as it is at the moment. And so to keep this information, we have to keep this pointer around. But then there's a question, of course, what happens if there's a node, programmer wants to duplicate this node, so they just make a copy and they don't reset that pointer. If they reset that point, so they put nothing in this field, then what will happen on marshalling back, we just create a new version for the newly created node, which is exactly what we want. But we can't enforce using types or anything, at least, I mean, if you have any ideas, let me know, any constraint on there's only one version of this pointer. So we have to do something ad hoc if we ever come across two. So actually from a semantic point of view, although this seems simple, we just put in a maybe, but really it is actually the least clean of these three things. So Haskell is slated to get support for linear types. Maybe that can help here. We are currently in the process of kind of looking at that. Well, so overall, you can have your cutting edge, great graphics, animations in Haskell and in a purely functional manner. Thank you very much. Yes?
So, did you just say on the previous slide that there's no linearity in Haskell that you can explain?
So the Haskell's type system, as it stands at the moment, has no support for linear types. There is, however, a proposal by a few people, including Simon P.J., on adding this functionality. Originally modified it on the basis of implementing like low-level code where you want to avoid duplicating resources. but I think it's applicable to this situation as well.
So, for example, if you have the uniqueness times clean, that would be good enough for you?
Maybe if I suppose clean uniqueness times would be fine too.
Yeah, so it's less than a week. So you use 0 for one time.
Yeah. Yeah.
You don't have to use it.
Yeah. So.
Well, in this case, you have to free it if you don't use it, so then you're much better than that.
So freeing is no problem here because we track all foreign pointers have finalizers, and we Objective-C use a reference counting scheme called ARC, and we use finalizers to adjust reference counts in ARC. So that's fine. I mean, I believe, just without having tried it, I believe clean's uniqueness types should be up to this job. Yes.
As I know, I mean, C does cardinality. That's computes uniqueness information.
Yes, I'm not sure what the current. No, it doesn't expose it, and I'm not sure how how much this cardinality analysis is used at the moment. Okay. Yeah, but it's here we need. Pardon? No. That's the problem. There's no way at the moment, like it would be in clean, to have a constraint in a type signature.
So it's before it's analyzed, and
that's right. Yeah.
It's not transported back to the program. But
Yeah.
of course, in clean, it's types are actually part of the service that type. So that
Yeah.
program replacement.
Yeah, in clean, in a type signature, you can put exclamation marks, I believe, before things, and then. Pardon?
I think you use U. I'm trying to remember the
It's exclamation mark, isn't it? Yeah. Yes?
One of the things that seems like it would be annoying once you get to very deep graphs is obviously like kind of unzipping all your structures, getting out of the computation. Do you find that practically speaking things like traversals or lenses or something ends up being a useful way of going from the scheme as a whole to into the individual slides?
So specifically speaking, so the question is whether something like lens would be useful to traverse the tree. Now, generally, yes. In the case of SpriteKit, this support for actions already kind of takes care of that, because you can run an action on a specific node. So these nodes can be named, and then you can, and that's what typically how SpriteKit programs are written anyway. I mean, this is not Haskell specific. So you use you attach an action to a node, which then on being marshaled back is created on this underlying data structure. And so for example, this action may be do apply an additional force to the lambda node, and then that action is applied on that node. And so the traversal is done by SpriteKit internally and not actually exposed to the program. But I mean, this is specific to SpriteKit setup of the action system. Mm-hmm.
So maybe one thing I've noticed that, so if you have a bake-in and steam dance, you have this wafer linear component. And I think this is actually meant if you program in E is also Haskell.
Yeah. So this is kind of getting into a philosophical point, namely, in this particular API, what I hopefully has become clear is we really tried hard to keep it really simple. It's functions, types, records, that's it. There's there are a few type classes, there's no GADTs, no type families, not this kind of 10 lists of GFC extensions at the top of the list. I think maybe something like that. There's some other ideas how we could maybe make the interface a little smarter at the expense of clarity. Now, I think something like that is a really nice tool for beginners to kind of, in a playful way, kind of get into Haskell, and hence the decision to keep it simple. I'm not saying one or the other is better. I'm just saying in this particular case here, the desire was to stay away from sophisticated language extensions, even not use the I/O monad or other monadic interfaces in the API, just to keep it more accessible.
Does Haskell SpriteKit run on the iOS?
In theory, yes. The practical problem in, can I just check it out of GitHub and compile it, is the cross-compiler for iOS in its current version doesn't support template Haskell. And the inline Objective-C, so not the Haskell SpriteKit binding, but the inline Objective-C stuff does use template Haskell. So there are some tricks. Pardon? Template Haskell is a meta-programming system for Haskell. So there are workarounds how you can kind of compile template Haskell stuff to iOS, and that could be, I haven't done it because it's painful, but that could be used. Otherwise, there is work on supporting template Haskell in GHC cross-compilers. At the moment, once that's done, this could be used in iOS, so it's not Mac specific.
And ultimately target the same LLVM bytecode Objective-C does?
So GHC's cross-compiler for iOS uses LLVM as a backend.
So Apple shouldn't reject it if it's the App Store is working Haskell.
Oh, I'm pretty sure this would work. I mean, the application you saw in the demos is a Mac app called Haskell for Mac, and it's in the App Store, and it has all this stuff in it, and Apple has never had a problem with that. Yeah. Ryan? You're right.
Lenses not make the cut in terms of simplicity?
Lenses?
Yeah.
Have you ever looked at the type errors? This is a rhetoric question.
Yeah. The reason I ask is that when we teach with the How Does That Programs curriculum, when we teach CS 101,
yeah,
with the Racket Universe package, it uses this very similar model of world updates.
Okay.
But I cringe when I see the students code for functional updates without lenses, because they've got 3 levels of structs, and they want to modify something that's 3 levels down, and they produce this enormous amount of boilerplate code to take apart and reconstruct different parts. They don't even have the functional update syntax in the student language. So that's one little bit of code that just makes me cringe, because it would be so much clearer if it were written in imperative code.
Yeah, but this is similar to Chris' point. So the action, apply action on nodes feature of SpriteKit, so this is really SpriteKit specific, really takes away most of this pain, because what I usually do, like in the example of spawn pipes, you have a custom action which you tell SpriteKit, apply it to this specific node. And then walking the tree, doing the update and making sure the tree is still okay, is done by SpriteKit behind the scene, and it's not visible in the Haskell code. Otherwise, you're totally right.
You don't typically do very deep.
That's right. Typically, you're quite shallow. Yeah. Okay.
About the linearity, just one final comment. There is a Docker code in the linear version of GHC, so it's a one-liner to try it out.
Oh yeah. So Ryan is one of the people who are behind this work. I should have pointed this out.
The prototype is not ready for prime time, but it's clear.
Yeah. Okay. Thank you so much. Enjoy the party.